Good morning. Who have I got from DI?
Hello, this is Aziz. I'm not from DI, but I happen to be logged in with their account because I was teaching a class.
Okay, yeah.
So I just happens to be logged in, so that's why it says that. I'll show you my face. Hello.
Hey, nice
Hey,
mic.
thank you. I'm an instructor with DI, not officially like an employee like these like.
No, I do this. I do the exact same thing. I'm a contractor with them.
Right. So I saw your post on the channel. So yeah, I'm interested in this topic.
Nice, welcome.
Yeah, thank you. Thank you for doing this.
My pleasure. We'll probably wait about 5 or 6 more minutes. People show up late to these things.
Sure.
Oh yeah.
I'll just log out and maybe log back in with my login.
Whatever makes you happy. I don't mind.
Okay. Sure, I'll be back.
Hey, Brian.
Hello.
How's it going this morning?
Good. How are you, Tyler?
I'm well. Welcome back.
Thank you.
That other person is going to log on a different account. He was using some corporate account. And, you know, as usual, we'll wait another 5 minutes, see what's up.
Hey, I was having trouble getting Box 2D installed.
Yeah, you will not need it until only for the reinforcement learning stuff, which we won't do any of today, but I also had trouble getting Box 2D installed several times. It's a pain in the ass. What kind of errors are you getting right now?
I tried to go the brew route like you posted on the README,
Mm-hmm.
and I'm getting a really weird error related to being on Catalina.
Oh, you know what? I don't think I've tried to run the reinforcement learning stuff since I upgraded to Catalina, so I might have that same problem later.
Catalina blew up my whole environment when I upgraded it. Like it completely rerouted all my paths. It was a nightmare. It took me a solid 2 days just to figure out how to get that working.
What a nightmare.
Yeah. Yeah, that's horrible.
Yeah, but so Box 2D, I can show you in one sec. It's only really necessary for deep reinforcement learning and reinforcement learning. One of the games in there is a physics game, the Lunar Lander game.
Okay.
Today we're only talking about, you know, the very basic intro to deep learning. So if you want to do these things on your own, I probably should try and install those too. I'm not going to teach these topics even in the full class this time around. We replaced them with generative adversarial networks and like a product kind of lesson.
Okay.
But send me your errors in email and I'd be interested in talking about them and trying to figure them out. I probably do need to install it anyway.
Yeah, we'll do.
How familiar are you two with just machine learning concepts in general?
Pretty.
Not much.
Not very, okay.
So I'll be really beginner on this topic.
Cool. Whew.
Tyler, what's your email address?
Teb@tebslab.com. I'll send it in chat. There's a hyphen. I regret buying the domain name with the hyphen a little bit, but I mean, I got the other one. I also own Teb's Lab without a hyphen, but that looks like Teb Slab. No one will ever say Teb's Lab.
Yeah. Are we gonna get these slides?
No slides. This is just written on my iPad, and then everything else I'm going to show is part of the GitHub resources. Did you see those?
No, I did not, but I know that you posted it from where I registered.
Cool. I just sent it into chat, and there's some easy examples. If you scroll down, I'll get this on the screen too, actually. I think I shared my wrong screen. So if you scroll down to the part using Google Colab, it's really, really easy to run today's notebooks on Google Colab. They come with all the proper dependencies pre-installed, and they can open it straight from GitHub. So you basically go to Colab, you say, open something from the GitHub tab. Yes, yes, you're allowed to use my GitHub account. And then basically you paste the URL here. So tabs lab will work here, and you can find Intro to Deep Learning. Open the first one. Boom. And these are the materials I use to present, which is just over here on, regular Jupyter Notebook running on my machine.
Uh-huh.
Plus, Google Colab gives you access to a nice little GPU. Might be faster than your machine. Fancy, fancy. Might not be. I feel like they're kind of shitty GPUs. They're free, but. Okay, so it's 6 after. We can go ahead and just start. Anyone who shows up late, they'll miss some content. Natural consequence of being late. So, Aziz, you said you're not super familiar with machine learning. Artificial intelligence in general, have you done any?
No.
Cool. Well, it looks like this, right? Artificial intelligence is a big, big, big field. Machine learning is a subfield within artificial intelligence, and deep learning is a particular variety of model that does machine learning. So Brian, you said you are pretty familiar. Do you want to kind of make a distinction for us between artificial intelligence and machine learning?
I know it can be different depending on how you look at it as well. Like I've also heard it like your first thing here, artificial intelligence encompassing all of machine learning. I've heard it the other way too, where they're separate. So machine learning, the way that I understand it, is using statistical models to predict some outcome based on a training set of criteria, whereas artificial intelligence is something where you're teaching the model something iteratively and it's learning on itself. And you can correct me if I'm wrong. That may be the definition for deep learning.
Yeah, I would say probably both of those I describe as machine learning, whereas classical artificial intelligence without machine learning is like experts hand coding algorithms to do stuff, that we'd typically think of as artificial intelligence. But it's also really tricky to pin down. One thing I've found in working in the field is like something stops becoming artificial intelligence in the public imagination as soon as we build a machine that can actually do it. So like if you go grab the classic text, Introduction to Artificial Intelligence by Peter Norvig, it's AI, a modern approach. Graph search is in there as artificial intelligence. So like A* heuristic-based graph search, which powers most likely Google Maps, that's considered artificial intelligence. Or, the chess playing AI, Deep Blue, that didn't use any machine learning at all. It was just a hand-coded algorithm that did like tree search. So it says, you're in this position, here's all the 50 moves you can make. That's the next layer of the tree. Okay, from each of those positions, here's the next 50 moves you can make from all of those positions in the tree. And experts came on and decided, they built a handcrafted algorithm that said, look at the state of a chessboard and tell me how advantageous that state is for the AI player. Is that a good state to be in or a bad state to be in? And they just did tree search and said, which of these, how can I get to the best state 10 moves from now? It's going to give me the most value. Okay. Whereas like AlphaGo, that was a deep learning, machine learning algorithm. It used a little bit of reinforcement learning as well as deep learning. And they had the machine learn by playing and losing and winning millions of games that evaluation function. What's a good state of the Go board? That was learned automatically. So that's kind of the way I think about the difference between artificial intelligence, classical artificial intelligence, and machine learning, which I absolutely consider to be a subset of artificial intelligence. Does that kind of make sense to y'all both?
Yeah.
Sure.
Okay, so this is the first objective, just kind of getting our terminology right, figuring out. And so deep learning is a particular kind of machine learning where you learn through examples. You learn by doing supervised learning in this case. Your machine learns through examples. And it's one particular kind of model called a neural network. Oh, I forgot, I have to apologize. There's probably going to be some people moving through and noise in the background soon. Long story short, we have to have an exterminator come over. There's a rat in our house, and this was the time that they could come. So I apologize for that. I think I heard him just knock on the door, but we're going to learn, and we're going to exterminate a rat.
Cool.
Okay, so this is what I was saying about traditional AI, right? Your AI engineers, in a historical case like the Deep Blue case, hand code the entirety of the decision-making algorithm. So they say, look, my inputs are the state of a chessboard, right? The algorithm is then going to take that state of the chessboard and make a decision, make a move, and that's going to, produce some outcome. And then in something like Deep Blue, it goes back and says, well, that outcome resulted in new input because my opponent made a move, and now I'm going to make a new decision based on that new move. In a system like supervised learning, which is one subset of machine learning, in supervised learning, you have answers to a question. You have millions of samples of answers to a question, and you produce some kind of model, which is like a template. In our case, it'll be a template for a math function, which we think will map some input data to some output label. So with the chess example, this would be like the state of a chessboard, and the label for your training data would be, the value of that chess state. This is 100% likely to lead to a victory in one move. This is 10% likely to lead to a loss in 2 moves, something like that. So your input data would be the state of the chessboard, and your input labels would be something like the value of that chessboard. And then you train a model using those data, and the trained model receives inputs, new inputs that it might not have seen before, new chess states, new chessboards that it's never seen before and doesn't specifically know the answer to. And it will say, okay, here's the value of that chessboard, make a decision, so on and so forth. But so the difference here is that the engineer doesn't actually specifically make decisions that lead to the decisions that the AI makes. There is a stage called training that happens right here with all this training data to tell the model, mathematically through iterative processes. In our case, the training is like gradient descent based. You guys both know gradient descent?
No.
Okay. Do you remember the gradient from calculus?
Yes.
Okay, sweet. So the way neural networks train is through a kind of gradient descent process, which is like iteratively finding the minima in some function. So, you have this point here, you have some function, the gradient is going to be in this direction. So, we take one step in that direction, and then we adjust our weights, we adjust our function to move it one more step further in this direction. And all of this is going to be hidden from us inside of the Keras library, so we don't have to implement any of gradient descent or anything like that. But the idea of minimizing our loss function, which is something I'll describe again in the future, so probably we're jumping the gun with gradient descent, but minimizing the loss function through this process is what happens in training data, or in the training process. Okay, and so the example that we're going to use to make things really concrete rather than a little bit abstract with the chess example, later today I'm going to have you build a neural network that takes pictures of handwritten digits. People wrote like 8, and they said, this is an 8. So the image of the handwritten 8 is the training data. The training label is the actual value of the, what the person said they were trying to draw. I drew an 8. Okay. People painstakingly compiled this into 70,000 images of handwritten drawings. And our model is going to train on these handwritten drawings with these known labels. And then later, once it's trained, it'll be able to recognize with high accuracy even samples of images that it's never seen before.
Okay.
How do we feel about this? You want to ask some questions?
That sounds really great.
Okay.
I'm scared. Will I be able to do it?
Oh, don't be scared. You'll be able to do it. You'll totally be able to do it. The code is remarkably easy now. And the intuition, you get there in time. Okay, so let's clear this off. So neural networks have been especially good at a few certain kinds of tasks. So there's lots of different machine learning models. Maybe you've heard of some, maybe you haven't, like K-nearest neighbors comes to mind. K-means is another popular algorithm. Decision trees, random forests, gradient boosted machines. These are all pretty popular. These are different examples of machine learning models that aren't neural networks. And neural networks are really good at two kinds of tasks. They're good at other kinds of tasks too, but these two are the places where it's really pushed the state of the art beyond what other models are capable of. And that is image processing, image and video processing type tasks, so computer vision, and natural language processing. So recognizing hearing text and turning it into, some kind of meaningful model of what that text means. Same thing with audio processing. Neural networks are doing pretty good at listening to audio and then transcribing it to the text. So they're really great at working with what's called unstructured data, which is kind of contrasted with tabular data, which is anything that's in your SQL database, basically. If it's got rows and columns and you can fit it in a spreadsheet, you've probably got structured tabular data. And there's typically better models than neural networks to work with because we can use statistics to really deeply understand those problems. Whereas with like an image, let's say I asked you to hand code an algorithm that could tell me whether or not a bird was in an image. How would you do that? Does it sound annoyingly hard?
A little.
Not the way you're explaining it. You're explaining if we can teach with 75, let's say, samples of 8, and it can recognize those patterns, then the bird would be the same.
Heck yeah, if we can do this, then it's not so bad. But if we have to, as the engineer, ourselves, let's give this guy some red eyes and a frown. If we have to decide what features about that image matter in making something like a bird, then our process is going to be something like this. Okay, I'm going to first perform a transform on the image that finds out where the lines are. Then I'm going to produce some kind of algorithm that can look at those lines and tell me what are the kinds of shapes that there are. Then I'm going to do an algorithm that's got all the shapes on the page and try to do a beak classifier. I'm going to try and extract if there's a beak or if there's wings or if there's feathers. Separately, I'm going to be like, you know what? Certain colors are popular in birds. I'm going to extract features related to what colors there are in all of these images. And if there's lots of bird colors, I'll push the probability up that there's lots of bird colors. So I would have to extract all the relevant features myself, then make an algorithm that says, oh, okay, I've got a 0.8 on the beak probability. I've got a 0.9 on the wing probability. I'm going to say that motherfucker's a bird. The colors are wrong, but I'm still really, really sure.
Yeah.
Whereas with supervised learning, we don't have to do any of this feature extraction by hand. Now, you still can. You can still do feature extraction with neural nets and say, like, I know that some aspects of the data are going to be relevant and some are not going to be relevant, or do a little feature engineering. I've got some data and I want to tell my neural network more. But in general, and what we're going to do today, we just give it a bunch of raw images, unprocessed. We say, here's the picture. This is a picture of a 1. And we train it on 60,000 images. We train it like 10 times on each image. And it learns to do this feature extraction by itself. So one of the big benefits of machine learning is that our models are flexible feature extractors. That's kind of their purpose. That's how they act. So they grab out the features automatically and kind of in a way that is really uninterpretable by humans, unfortunately. So that's the downside. But the machine learns the features on its own. It can't really tell us why it's making its decision, or I mean, more importantly, we can't understand its decision because its brain is too weird and complex for us to think about, which is kind of true of our own brains, right? We don't know why we make the decisions that we make, so fair enough. But we'll train it, and then it'll turn out to be really, really good at recognizing handwritten digits, and we will never have had to think about, like, what are the properties of an image that make something an 8 or a 0, and how do I tell if it's an 8 or a 0? I don't have to grab out two circles. I don't have to put the position of the circle somewhere relative to the rest of the image. It just happens by magic. Well, by math, but same thing.
Okay.
So let's pause again for questions here. This is the major benefit of AI. We're talking about one specific kind of machine learning called supervised learning.
Okay. So supervised learning is machine learning,
Right.
and traditional AI would be the outer circle, and supervised learning is one type of the subset of AI. And so these models, or this training untrained model, are there libraries, or like what kind of algorithm, or this brain? This sounds pretty intelligent to kind of recognize based on raw data. Who makes that, or who made that, and what is that piece?
Perfect. Yeah. Okay, so the untrained models are, in our case, a specific kind of model called neural networks. The libraries, there are lots of popular libraries you've heard of for building these things. TensorFlow is one, Keras is one, PyTorch is one. We're going to be using Keras today. And I think the next thing on the list here is to talk about the mathematics of how the neural network is constructed. So what is a neural network? And I'm going to say the disappointing thing out loud that lots of AI hypists don't want you to know. A neural network is just a math function. That's it. It is a really complex math function, and you can construct, infinitely many different kinds of neural networks. So it's really like a structure for a math function. And it's so complex that we use something called a computational graph to help us think about what the math function represents. So first I'm going to show you a simple example of a, quote, computational graph. It's just a way of representing functions. So here's our function with 3 parameters. The function of x, y, z is x plus y times z. And the nodes on the very left, I think I just froze. The nodes on the very left, yep, I'm still freezing.
No, you're fine. I can hear you.
Oh, okay.
You froze a bit before, but I can follow.
So the nodes on the very left are your input nodes here, and they just hold the input values. They have an edge to whatever their particular relevant combination is. Whoa, I don't know why that happened. So x and y get sent to an addition node. The result of 1 plus 2 is 3. Z, this 3, gets sent to a multiplication node along with the result of this addition. 3 times 3 is 9. Okay, so this is maybe a little overly complex when we could have just written this. I think right now most of us are probably perfectly comfortable with this notation. We understand what it means. But in neural networks, we use the computational graph because our neural networks are densely, deeply connected like this. So let's say these here are our input nodes, and we have some data. In our case, this is going to be a pixel each here. When we finally process our handwritten digits of, an 8, then what we're going to do is flatten this. So, the first row is going to be the first row of our input vector. And the second row of pixels is going to be the second row of our input vector. Okay, we're going to flatten the data. That data is going to be represented by 1 pixel each in the input layer of our neural network. And the value of that pixel is going to be sent as output to every node in the second layer. And that second layer is called the first hidden layer. So the input layer and the output layer in a neural network are called the visible layers. And everything in between the input and output layers are called the hidden layers. The output layer is going to represent our prediction. So whether or not this is a 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0. And the input layer is the data, the pixel data. Okay. So I need.
Okay, 1 second. Let me understand this. So you took the first row of 8, which will have many dots. Let's say it's a very unpixelated or pixelated image. So let's say it's got just 3 pixels right on top.
Okay.
So those 3 pixels is one. Those 3 pixels in the row is one row. Like what is the first circle representing in the graph?
The top left
First.
pixel, right here, this one.
Oh, so one circle is 1 pixel.
Exactly.
Okay, got it. And so this row, the column is the pixels of the row. So 3 pixels in the column of. This is the first one. The where your mouse is basically the top right pixel. Correct?
Yeah. Let me make sure I understand. This here that I'm coloring in yellow.
Yeah.
Is representative of, this first pixel.
Right.
Okay. And let's say in our case, there's going to be 28 by 28 pixels in these images.
Sure.
Which means our input vector is going to be 28 times 28, which is 784, I think.
Got it.
784 pixels total. So there'll be 784 circles.
On the first row altogether. Oh, okay, that's good that I asked that question because I didn't think it that way. Okay, and the right-hand side column of the circles, the output pixel representation is going to be what we say, hey, this is what really 8 is. Correct?
Exactly, and we will have 10 of them in our case because we're able to make 10 different predictions. We're calling it a 0, a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, or a 10. Or a 0.
Oh, so the numbers. Okay, so not just 8. It can predict 1 and 2s and 3s and 4s as well.
Exactly.
Oh, wow. I thought we were only predicting 8s only. So you're saying that we could start with giving them only 8s and it would recognize all 10 numbers?
No, we'll give them examples of everything that we want them to be able to predict.
Of course. Okay. That would be magical if.
Yeah, that would be magic.
Okay. Okay, cool. So we give them different numbers, 75,000 of them, 75 of them, and it can predict all the digits. Got it.
Exactly.
And the middle layer is the hidden where the predictions are gonna, and combinations, the magic part or maths part's gonna happen. Okay.
Exactly. And let's zoom in on one. Well, I won't erase everything. I'll just erase the stuff that's positional. Okay, boom, 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 boom. Unannotate. And each of these, each of the nodes in the hidden layer processes the data in this same way. They all take all the incoming data from all their incoming edges and sum it up. And then they send the result of that sum to what's called an activation function. And the sigmoid function is a particular function. It's like the oldest first activation function that was ever used, but there's lots of popular activation functions now. And here, whoa, it is so ugly with those annotations. But in the second folder of this repo, there's a list of many, many different activation functions. So we're not talking about all the different activation functions that you can have today, but you can kind of do this on your own after class and look at some of the other activation functions that have become popular. Okay, but so we add up all the data, we add up all the inbound edges, and then we send it to an activation function, and then the result of that activation function goes out to the next layer in the neural network. And so in our specific case, that information gets sent to the output layer, but what makes a deep neural network is having many hidden layers. So in a deep neural network, in all likelihood, the result of this sigmoid function is getting sent to another layer that processes it very similar to this one. It takes it in, it sums everything up, it performs an activation function, and sends the result of that activation out. And this is modeled on human neurons. This is a lot like how human neurons behave, which is why these things are called neural networks. In human neurons, electrical energy in your brain gets sent to a particular neuron, and that can come from many synapses that are connected to that neuron. And if the activation energy is high enough, then your neuron activates and sends its energy along other synapses. So that neuron is said to have fired. Okay, but aside from that, the model between the human brain and this brain starts to break down pretty significantly. So it's more like inspired by rather than based on. Okay, so let's zoom in one more layer. So right now we have the general structure, but what we don't have is any mechanism to tune this mathematical model. So we're going to be able to build complex constructions of graphs like this, but we need some parameters in those graphs that we can fine tune during the training process. Okay, and now it is time to actually clear these. So zooming in just one level further on each individual neuron, we have the introduction of these weight nodes, and this bias nodes. Okay, so the output from your previous layer actually gets multiplied by some weight. Okay, and this weight is initially, when you build your neural network, it's initially set to just a totally random value. And as you go through the training process, the weights and this bias here, which gets added to the sum after all the weighted inputs, are fine-tuned by gradient descent during the training process. So intuitively, it's like we see a picture of a 1, our neural network calls it a 5. We say, that's wrong, change your weights and biases. So we adjust them. And if we do a batch of images, we say we look at 100 images at once, and we were wrong about all of them, we adjust our weights and biases a lot, by a big amount. And if we were right about 99 of them and wrong about 1, then we just adjust them a little bit. Okay?
So Tyler, in a deep neural network, how are we telling the weights what to do, or is this something that's done in just a single layer neural network where we're telling it, hey, that was wrong, and we change the weights on our own?
No, it's all an automated process, and it's all via gradient descent and something called backpropagation. So one sec, let me go to the whiteboard here. It's turned off. Okay. Where is that window? There we go. Okay, so let's say we've got our neural network. We've got our, 784 little input pixels. We've got several layers, and who knows how many nodes there are. Let's say we did like 256 nodes in the first layer. Whoops. And then we did 128 nodes in the second layer, and then 64 nodes in the third layer, because we're nerds who like powers of 2, or at least I am. And then finally we have our output layer, right? And our output layer has the 10 nodes in it. We're going to use something called a loss function in order to quantify how poorly or how well our neural network does. So basically, the way it works is we've got in total 60,000 of these image inputs. This is the actual number for the mnist dataset that we're going to use. In a real world situation, we might have millions, or we might have tens of thousands, or we might have a really small number, but then we're not going to do very well. You need a lot of training data to make these things work. We're going to run this process in batches. We're going to say select something like 100, some batch size, and this is a parameter that you can tune during your training process. You can have a larger or a smaller batch size. I'm going to say take 100 images and just send them through the network. Do the math. Give me 100 outputs. And then, since we have the true labels, right, we're going to get 100 predictions, and we have 100 true answers. We're going to use a function. The function we're going to use is called Categorical cross entropy. And this is a function from the world of information theory. And basically, it's going to say the categorical cross entropy looks at our prediction. So let's say our prediction was that a particular image was a 5. Then our output is going to look like 0, 0, 0, 0, 1, 2, 0, 1, 2, 3, 4, 5, 0, 0, 0, 0, 0. So we're going to, this is called a one hot encoded vector,
Yep.
which we'll talk about again in a second. But basically, it's like we turn on the value for 5 and we turn off all the other values. In reality, our prediction is going to look more like, 0.1, 0.1, 0.01, 0.1, 0.7. So we're going to say, it's 70% probability that it's a 5. And our, if it was actually a 1, then the true labels are going to look like it wasn't a 0, it was a 1, and it wasn't anything else. And so categorical cross entropy is going to look at, for the field which was the true answer, how wrong was your prediction? And in our case, our prediction was as wrong as it can be. We predicted 0% probability that it was a 1, and so, we're off by 1. And that's a big deal. So we're going to perform that computation. So the categorical cross entropy for this would be more or less 1. The exact mathematics of it aren't too important. There is another notebook later on where you can look at categorical cross entropy and what exactly it's doing. But anyway, that's bad, and we send backwards this information. We propagate backwards. You were off by 1. And the process of that backwards propagation is that we are actually computing the gradient. We are computing the partial gradient with respect to every single individual bias and weight value in this complex math function. The algorithm that was figured out that made this possible is called backpropagation, but it's just a clever way of partially computing via the chain rule the gradient with respect to each of these weights and biases for the loss function. That is to say, the loss function is categorical cross entropy, the difference between our predictions and the true labels that we know. And we compute the gradient, which is, the direction of maximum descent according to that loss surface, which direction we should update each individual bias and weight.
Okay, and so this is only happening on the last layer before the output.
No, it gets backpropagated all the way through. So we say
But it's only happening once you get to an output, and then it backpropagates across. It's not happening at each individual layer and saying, oh, I'm checking what the answer was at that point and then updating going forward.
Yes, that's exactly correct. That's correct. And not only do we don't typically do it after one image, we compute the loss function on like this batch of 100 images. We say compute 100 predictions first, aggregate the categorical cross entropy scores for each of those 100, and then backpropagate that batch of 100.
Okay. Got it. That helps.
Sweet. And this, this whole process is done automatically for us. We don't have to hand code this anymore. 10 years ago, you would have had to hand code this if you wanted to do any real research in neural networks, before TensorFlow, before Keras. And that was a pain in the ass. Nobody liked that world. So we got rid of it. Okay, so the result of this entire whole conversation is basically this image is the foundation of every little neuron. We're going to put hundreds of thousands of neurons sometimes into a neural network, but at the end of the day, it's just a really complicated math function that we're going to, we are essentially, when we're using a neural network, we are asserting that there is some math function that approximates the relationship between our input data and our output label. In our case, a picture of an 8 and the value 8. We're asserting that there is some math function that approximates that relationship. And neural networks, one thing you can prove about neural networks, this particular construction, is that as long as this activation function is a non-linear function, it's not just a line with a slope, it's anything other than that, then these constructions are universal function approximators. That is, they can approximate any function that exists. You can create a neural network that will map to any other math function you can possibly create, within some small error bound. And that's why they're popular, is because we can basically say, we can assert, as long as it's the case that there is some underlying true math function, a neural network can approximate that math function. We can build a neural network that will approximate that math function. Okay, so after this, we're going to jump into actually building our first neural network in Keras. So this is a good time. We'll still explore a little bit more of the theory because there's a few terms we haven't introduced, but this is a good time for questions, comments, thoughts.
I've got a couple questions. The first one is, how do you determine the dimensions of the hidden layers and how many hidden layers that you have? Is it just whatever kind of higher decision that will affect what you make?
Yeah, so there are a few like rules of thumb, but unfortunately this is a place where, or maybe fortunately, depending on how you think of it, I mean, it's kind of exciting, but the engineering is way ahead of the theory in this particular case. So knowing how many layers to do and how many nodes to put in each layer it has been a process of experimentation. Some rules of thumb are like, your first hidden layer should be somewhere between like 1/3 to 2/3 the size of your input layer. You typically don't want to way over parameterize. So you've got 784 pieces of data that are relevant. You don't want 10,000 nodes in your first hidden layer, right? Because you're just saying, well, do I really have 10,000 pieces of information out of those 784 pieces of information? So common structures for neural networks include like shrinking. You go from 784, like I kind of said before, 784 to 256 to 128, and you kind of compress the data into a smaller representation and then try and do your output. Actually, one really useful, I'm trying to get a new tab here, neural network zoo. Why did you take my focus away? So the Asimov Institute here, let me clear this, has a lot of collections of popular architectures for neural networks. So, like an autoencoder goes small and then blows up. You've got some networks like the deep convolutional neural networks, you see that same structure, they kind of force it into a smaller representation and then have denser connections here, and then they kind of go back up. These are your very basic neural networks. This one, you kind of see a small expansion and then you just keep it flat and then compress down when it's prediction time. So there's all kinds of weird and wacky things people have done, like the capsule network, really interesting. Deep residuals, you just keep on keeping your network flat, but you just do a lot of it. But unfortunately, it's really hard to know beforehand which kind of structure for your neural network is going to be successful. Does that make sense?
Yeah. Does this website have explanations as to like what these different kinds of networks have been commonly used for, or where they've been successful, that kind of stuff?
Yeah, totally, absolutely. And they've linked to papers where these first things were described, and it's a really useful resource. And then, it's also worth saying here that in addition to the like shape, there are different kinds of nodes that we haven't introduced yet, like convolutional neural networks do something that's somewhat different from the math that we just talked about, where at each layer, instead of doing this kind of thing, you actually have a kernel, like a 3x3 image kernel that you scan across the entire image and then produce an output that you add to a activation function and send forward. And recurrent neural networks with long short-term memory nodes do something slightly different than that too. So some of the architecture is not fully captured. Like what you have to see is the difference between these colors of nodes. These different colored nodes do something slightly different, or sometimes very different, from exactly the node that we described here. So this is, neural networks 101, but there's also other kinds of nodes that are powerful and helpful.
Gotcha. The second thing I was going to ask is, how prone are these types of neural networks to overfitting to the training?
Extremely. It is really easy to overfit your network. And the thing about it is they're always way over parameterized. Like at the end of the day, your number of parameters are these weights and this bias. If I have, I'll just show you right here, if I build a neural network that is input from the mnist, 784 pixels, it's got a single hidden layer with 32 nodes in it, and then it's got an output layer with the 10 nodes for our classification in it. That's 25,000 parameters, 25,450 parameters that are tunable just right there, right? And the math for this is fairly straightforward. Let me go right here. This is just, right, 700, oops, I'm not on annotation mode. This is just 784 nodes in the first layer times 32 nodes in the second layer, plus 32 nodes plus 10 for their biases. And then, the next layer is there's 32 nodes, so 32 times 10 nodes in the second layer, in the output layer, plus those 10 bias nodes in that layer. And that's how you get to 25,450 nodes. Super modern neural networks, like the ones that are crushing benchmarks on Imagenet or, publishing new papers today, they have millions of parameters, easily, multi-millions of parameters. So that also makes the expensive really training really expensive, makes the expensive really training, wow. So, training them can be really expensive and costly, and it also means you're prone to overfitting. So you got to be pretty careful. You got to watch your curves. You got to say, have a good amount of validation data. And that's one of the other reasons why you want so much data for these. We're looking at 60,000 images and we have 10,000 held out for test data. And we're still going to make like 20% of it validation data of the 60,000 images. Aziz, you said you're not really familiar with machine learning. Do those validation, test, and training data mean anything to you?
Yeah, I'm following that part.
Okay.
I do have clarification questions on what happens. Like, finish your thought and I'll ask the question.
I think I'm finished.
I'm following. Sorry?
I said I think I was finished, yeah.
Okay, good. So my question is, so the hidden layers. So we start with the input one image, start with one of them, and then it does some kind of computation to. So what I'm missing is, like, when there are multiple layers in the middle, the hidden layers. It feels like in certain models, the hidden layers do computations towards something, and then it does computations towards mapping to the outcome.
Mm-hmm.
So I'm missing that what is really happening on those individual layers. Like the individual nodes have to know the inputs and outputs both to know what it's working towards, correct?
Yes and no. So the nodes all work together through that backpropagation process. So they all get information once they've made a bunch of predictions and we've computed the loss function, categorical cross entropy. Then they all get information that flows backwards about what their contribution to that error was. That's an okay way to think about it. That's how most of the mathematicians think about it. It's maybe not entirely true, but it's a very useful mental model. So each of the weights and biases at each layer, that data flows all the way back through it. But I think another thing that you're kind of asking about is what's the job of each of those layers? If we have so many, what are they all doing?
Yeah,
And
what are they
so,
working towards? Like if yeah, go ahead.
yeah.
Maybe.
So what a lot of people say, and again, the theory on this is not 100% solid, but empirically, oh wow, check that out. That was sweet. But empirically, we think we have some evidence to suggest that the early layers are doing slightly different things than the later layers, right? Because so this layer is 1 degree of mathematical computation removed from the actual input itself. It can only really know things that are fairly specific to the nodes. And so we say this is like basic feature extraction. This layer might know where the lines are. And then by this layer, some of the nodes might be representative of different things that lines can do. This is where I've found curvy lines. Maybe these ones tell you something about where there's curvy lines, and these ones tell you something about where there's edges, like sharp edges, corners. And then as you go later and later, you get higher level features. Higher level features like these 3 tell you something about where there's eye shapes. Or for mnist, maybe eyes isn't good because that's more like looking for animals. For these, it tells you where there's, 6s, a curve with a circle, 6s and 9s maybe. And then these 2 tell you where there's, more liney things like 1s, 7s, okay, that kind of thing. And then finally, they get combined into their final 10, which tell you very explicitly, we think this one's a 0, we think this one's a 1, we think this one's a 2, so on. But the frustrating part of this answer is we don't actually know. You might have heard that these things are often called black boxes. These are black box models, and it's incredibly difficult. I don't think any human on Earth could say, okay, turn this graphical representation of our neural network into an actual math function, and I will tell you what each of those parameters means. I will tell you what, weight 152 here. Yes, weight 152 here is telling you about the, 6ness of, we just don't know.
So how can somebody create this model without knowing what it does?
It's the beauty of the training process, basically. The machine knows how to get closer and closer to a correct answer, but it doesn't have to tell you how it got that answer. It just works.
Yeah, but what I'm wondering, the person who came up with that function, because what a neural network is really a function, a complex function. Somebody wrote that complex function though, right?
Well, they wrote a template for that function, right? They wrote a structure, how many nodes in each layer, how many layers, but they didn't do anything to define
Okay,
the weights. The
got it.
weights were just set randomly, and the first function, the function that the human actually, wrote, quote unquote, sucked. It made a bunch of guesses. It was wrong. And then the machine learning training process said, here's how to be less wrong and get slowly less wrong over time, slowly less wrong over time. And then after it gets less wrong over time enough times, it starts being right.
Got it. So some human wrote what you showed in the neural network zoo, the different models, those function models somebody wrote. And then the magic happens by the permutations, and not really the permutation is the wrong word, but the training process.
Exactly. And something that's, good to talk about here, this is a good segue, is like major architectures are released and you can retrain them to do different tasks. So let's say I release one architecture called MobileNet. I didn't spell that right, but we'll deal with it. I'll put a frowny face. Okay. MobileNet is a structure for a neural network, and we can take MobileNet and we can train it on the mnist dataset and then get a result. And our resulting neural network here is a trained network that's good at recognizing digits.
Got it.
But we
Okay.
could take that same neural network architecture and train it on a separate benchmark, one called Imagenet, which is a collection of things from the natural world: birds, humans, bicycles, computers. It's got 1,000 classes of thing, even like down to certain breeds of dogs and certain breeds of cats, stuff like this. And if we train it on that, we get out a different, it's the same structure, but it's a different neural network. And this one is good at recognizing, birds, cats, flowers. But we couldn't necessarily just swap them and say, now let's make the one that we trained on Imagenet be good at recognizing digits, because the weights and parameters that resulted from the training process are good at recognizing flowers and birds, not necessarily digits.
Right. Wow.
And this is actually really common to do. Take an architecture and train it on different data sets when you need to do different things. So some architectures are more specialized and appear to be better at certain things. So like there's some architectures where, you'd try this, you'd train it on mnist, and maybe it sucks, but it's still really good at recognizing flowers and digits. And there are some architectures, like there's really some specific architectures for the medical world, looking at like radiograph-based images and finding where cancers are, that don't seem to perform well on stuff like the Imagenet benchmark, which might tell us something interesting about the very different sorts of images that exist in the natural world if I'm just out there taking photos, and the types of images that are produced by radiographic scans.
This is fascinating.
It's totally amazing. I love it. And then there's one more thing while we're on this topic called transfer learning, where you can, and it's been shown to be quite effective. Let's say I train this thing and it's good, it's actually good at recognizing images. I can then retrain it, take the starting weights that it learned from learning how to recognize images as the starting point, rather than random values for the weights and parameters as a starting point. And I can do transfer learning. So start with a different beginning and train it on another data set, some other data set, like Imagenet here. And then this training process tends to be much shorter. If you use a neural network that's already trained on something else and you train it to do a new task, if it was good at whatever that old task was, it's often much easier to use that as a starting point to train it to do a new task, even though it's the same architecture. And there's some, tips and tricks on how to do that training process, because you do the training process a little bit differently when you do transfer learning. But anyway, that's a pretty advanced topic. Okay. Okay, here's what I think I want to do. We've been sitting in our chairs for, hey, Ryan Elston wants to join. I'll let you. Hey, Ryan, decent timing. I was just telling these folks, we've all been here for about an hour. I think it's a good time for a 5-minute break, stand up, use the bathroom, get a cup of coffee, wiggle your arms, whatever it takes. And then we're going to come back and work through this first notebook, which will be pre-processing our data so that it fits with our neural network architecture and we can actually, train some neural networks, building our first neural networks in Keras, training them, and visualizing some of our results. Okay?
Sounds good. How good do you have to be with Python? I've used it long time ago.
Not that good.
Okay.
Yeah, it's just, we're going to import a library. We're going to use the functions on that library. It's going to be groovy.
Okay, cool.
Ryan, are you there? No. That's
Hey
okay.
there.
Hey.
Yeah, I am here. I just now stumbled upon this link, so I was curious. Very, very far away from deep learning and Python and all that. So I'd love to stick around and watch. You guys,
Yes.
I'll
Stick
chime
around
in
and watch.
if I have any.
Sweet. And you may want to go go here to the materials and just try opening these on Google Colab. It'll be really useful to follow along. So I'll send this to the chat. And these instructions are halfway down the page. That's a good way to spend these 5 minutes while I'm getting myself a new cup of coffee.
All right, sounds good.
I was too slow. Okay. Okay, we got 2 out of 3. Ryan, I can't tell if you're there right now or not.
I'm here. I will be following along.
Sweet. Okay. So here we go. This is our first little piece of actual Python code. We're going to do 3 things in this first little lab. One, pre-process the data so that it fits with the computational structure that Keras requires and that neural networks generally require. 2, build a couple of neural networks using the Keras library, just simple ones. 3, train them. Okay, so that's the goal. After that, I have an exercise for you guys to work on while I'm here so I can help you answer questions, blah, 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 blah. And then there's most of the answers to the questions in this third notebook, which you can see. Okay, but so here's what we're doing now. Importing matplotlib, that's just a charting library. It's got nothing to do with machine learning, but it's useful to make charts. And then from the Keras library, we're importing our data set, mnist. This is the handwritten digits data set that I've been talking about. This is just a function provided by Keras to help us grab out the training and test images. So there's a 10,000 image test set and a 60,000 image training set. And this is the format that they give it to us in. They expect 2 tuples and we have to unpack it. And you can see here, the training set is 60,000 28 by 28 images, where each of these images is a NumPy 2-dimensional array. And then we're looking at an individual training label. The first training label is this number 5, and we're going to need to fix that. We're going to turn it into a hot encoded vector, but that in just a second. Okay, so here we're just loading up the data. Pretty simple. Keras is nice that way. In a real world situation, right, you're not just going to be able to call load data. You're going to have to painstakingly collect and curate your own data, fetch it from like a SQL database or something like that, or build your own tooling around grabbing the data. This is just some matplotlib code to show you what these images look like, right? Okay, so this is the first one we're being told that's a 5. This is a 5. You might be forgiven for thinking it's a 3, right? But this is what the data looks like. And each of these comes with its own labels. It's like 9 and 9. I think that one's a 4, but it could just as well be a 9. I think this is actually a 9, but it looks a lot like an 8, So all this to say, some of these are actually quite hard. This is a G, that's not a number, So this problem is actually a tricky problem that humans don't even crush all the time. Okay, but that's what the data looks like. There's 2 problems with the data from our perspective. So Ryan, you came late, you didn't see this, but this first one, we talked about, Aziz and Brian, you remember I said, like, we're going to process the 28 pixel by 28 pixel image into something that's flat. So we're going to say, take the first row of that data and turn it into a flat vector, then take the second row of that data and make that the second set, and then take the third row of that data and process it here. So we're just going to flatten a new participant. Hey, huge swarm. So we're just going to flatten that data. That's to solve this first problem. And this first problem is solely a computational one where we say, look, the Keras library expects the data in a particular format. That format is a flat vector. So we got to flatten the data in order to give it to Keras in order to do our computations on it. Okay, this second problem, then the labels we've been given are integer values, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. but we want to do a classification problem, not a regression problem. And what I mean here is, like, if our neural network gets in an input image that says, you know, it gets an image of a 6 and it says that that's a 9, that's not off by 3, right? It's just wrong. And it's not clear that, you know, saying it looks like a 9 versus it looks like a 5, in my mind, it's actually closer to being right if it's a 9 than it's a 5. So we definitely don't want to say a 9 is off by 3 and a 5 is off by 1. We just want to say both of these are wrong. Okay? And this is true of all classification problems. You know, if we were doing something like not classifying handwritten digits into a number, but classifying this is a bird or a cat or a dog, we wouldn't want to say bird is 0, cat is 1, dog is 2. And if you guess bird when you should have guessed dog, you're off by 2 instead of 1. That also doesn't make sense. So in classification problems, we always just want to say wrong is wrong, right is right, and there's no numerical, there's no ordering to the right or wrongness of the data. Okay, so we're going to solve this using something called a one-hot encoded vector. And Brian, I know you're familiar with these, so could you describe a one-hot encoded vector for us?
Yeah, a one-hot encoded vector is it's an array, or what it implements is an array of zeros or ones based on how many categories there are within the data set. So like if we're doing from 0 to 10, you know, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 options. And whether it's a 10, then the 10 space will be highlighted as a 1. If it's a 5, then the 5 space will be highlighted as a 1, and everything else will be zeros.
7, 8, 9. Yeah, absolutely. Okay, so we say our first value is the number 5. Our one-hot encoded vector for 5 is going to look like this: 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay, so we're going to change all of our input labels from integers into something that looks like this. Groovy?
Looks good.
Groovy. Okay, let's clear these out. Okay, so both of these are really easy to do with built-in tools in Keras. So to do the one-hot encoding, we're going to use the Keras utility toCategorical. This is the same line of code you saw above, just grabbing out the test data. This is the size of our image. We're going to reshape our images to be from 28 by 28 to being 28 times 28, 784 single length. And reshaping just looks like this. We call the built-in reshape function, and basically we say we're going from this shape, from the shape that it already is, to this shape, 784, the shape that we want it to be. And we just call that function, and it takes us from, you know, this kind of shape to this kind of shape. Really convenient. And you can see that processing worked here. Oh, Ryan's gone. Bye, Ryan. Okay, the second thing, toCategorical, we're going to say, here's the number of classes we've got, 10, 1 for each digit. And we're going to call the toCategorical function on the training labels and the test labels. So now this thing used to look, you know, it used to say 5. Now it's this one-hot encoded vector where it's saying it's not a 0, it's not a 1, it's not a 2, it's not a 3, it's not a 4, it is a 5, and it's not 7, 8, 9, or 0. Or sorry, 7, 8, or 9. Okay, so that's the pre-processing step. And this was all just to get our data into a format that the neural network is comfortable using, that it can do the mathematical processing it wants to do. How do we feel?
Looks good.
Yeah.
Okay.
Good.
Then let's build our first neural network, okay? There's two kinds of models in Keras, the sequential model and the functional model. The functional model is needed for more complex architectures where there's like connections that skip around and go ahead. we're going to just use the sequential model, which means each layer only sends data to the layer directly next to it. And that's not true in every neural network, but it is true of the first ones that were ever built, the basic ones that we're going to talk about today. So we're using the sequential model, and we only have one kind of layer, the dense layer, which is just exactly what we've been talking about. Single nodes that all do the sum to the activation function, where all of those nodes have an output connection to every node in a subsequent dense layer. So we're just going to make stacks of dense layers. And this is how we do it. We make a new model, and we iteratively call model.add for each new layer we want to create. And we create a model here. Okay. Units is how many nodes there are going to be in that layer. So we're saying we're going to have 32 nodes in the single hidden layer that we have. Activation is the activation function. We've only talked about the sigmoid activation function, which is kind of like an S-shaped curve. I don't know if you've ever seen, but a sigmoid function just kind of looks like this. Okay. And it's like the OG activation function. Another activation function that's really popular is called Rayleigh, Rectified Linear Unit. And it's looks like this, where it's 0 for everything below 0. It's just, a flat line. And then it's just the linear function, y equals x for everything above 0. So that's 0. This is actually more popular now than sigmoid, but sigmoid's kind of the classic original. And there's lots of other ones you can specify here. You can look up in the Keras documents everything that's built in. And sometimes people will even build like their own custom activation functions. I can't think of a good example offhand of why that would be necessary. Usually we just use something simple like Rayleigh. The trade-offs here are like Rayleigh's fast and easy to compute, and sigmoid has some problems when you get the data up here. The gradients are really small because the slope of the line is really small, so you kind of get really slow adjustments. It doesn't learn as fast often. And then this last parameter, input shape, this is only necessary on the first hidden layer. You just have to tell the neural network, because it doesn't know, right? We just said make a sequential model. It has to know how many nodes are going to be in the input layer. So we describe the input shape as being our 784 flat vector. And then subsequently, if we wanted to build something with 2 hidden layers, we'd call this model.add function again, and we wouldn't include this layer. I think there's an example of that below, so I'm not going to change this code. But okay, questions about these two?
Yeah. What makes you determine the units? Units are the number of nodes within one layer, correct?
Correct. And I chose 32 totally arbitrary for this example.
Got it. And how many layers get created is, the number of times you're going to add this.
That's right.
Added 1 layer so far.
Yep.
Okay.
Cool. And then we'll add a second layer, the output layer. And again, we're going to say units, this time number of classes. If you remember from above, that's 10, because that's how many predictions we want to make. That's the shape of our test labels, our one hot encoded vector. And the activation here is a function called Softmax. This is almost always used in classification problems. Your final layer will use a Softmax activation function. And what that does is it takes the raw values across your entire, whoops, I thought I was annotating. Takes the values across your 10 output nodes, which might be anything right now. Could be really, really high values, really, really small values. It could be any floating point, whatever the function created. And it normalizes them. So it says, take this and put, x divided by the sum of all of these, which means we'll end up with something that we can interpret as a probability. It's the share, it's the normalized weight that this particular thing got. So after we do this softmax activation function, all of the values in our output layer will be between 0 and 1, and they will sum to 1. And we interpret them as probabilities. So that's the purpose of the softmax activation function. And I've never seen a classifier, a neural network classifier, that doesn't use softmax as the activation function. Okay, let's erase this, and this. Let's just clear it all. We don't need those activation functions either. Okay. So actually, I'm gonna run these real quick because I forgot to, and we want to actually see the training process happen. It's more fun to watch it live. Okay, so once you've built a neural network, what do you mean image size is not defined? You there? Run this. Okay, run that. Yes, good. Okay.
Oh, you can run that in Jupyter?
Yeah, totally. So you can just run it with Shift Enter. We're gonna process our,
Nice.
recreate that, reprint the training label, still looks good. Okay, recreate the neural network. Now we've got a fresh, brand new neural network. And then here, once you've created the neural network, you have to compile it in order to prepare it to be run. And you have to choose an optimizer and a loss function. The loss function we talked about a lot, right? Categorical cross entropy, you can see here. And again, that just tells you how do you classify how wrong or right your model is. And these optimizers are all forms of gradient descent. SGD stands for stochastic gradient descent. But there's other ones too. And in this series, I think it is in this second section, there's some good reading about actually doing different optimizers and what they're all about. So yeah, optimizing gradient descent and different optimizers. These are useful if you want to learn more about what the difference between SGD and Atom and Attograd and all these other optimizer functions are. Basically, SGD, like sigmoid, is the original gangster, and there's been improvements that kind of help your models converge faster or learn faster under certain circumstances. And then the metrics here, this is just stuff that I, the human, want the machine to track during the process. So it's going to measure the accuracy and tell me how often was I correct, how often was my model wrong over both the training and validation data. And so these are only for the human, not for the training process, but you can keep a number of stuff. You know, you can also keep like your F1 score or your precision or your recall or any other custom metrics you can also define. But the most important thing to do is specify the optimizer and specify the loss function. And then to actually train the thing, actually do the training process, you call model.fit. You specify the data you need, the training data, the labels associated with that training data, and then some other stuff. So batch size is how many images to look at before you do a single back propagation, before you adjust the weights at all. So we're going to look at 128 images and perform a back propagation step to adjust our weights. Then we're going to look at 128 more images and do a back propagation step, adjust our weights. So the trade-offs here on batch size are like, if you do it every single time, if you just have like a batch size of 1, it takes a lot longer because back propagation is expensive and forward propagation is less expensive. If you have a really small batch size, your training might not be stable because you're adjusting the weights based on every single image. Whereas if you're adjusting the weights based on how well you did over 128 images rather than just each time, you get a little better stability. But if you have too many, you know, if your batch size is like 1,000, 10,000, you start losing the ability to kind of make fine-grained connections, fine-grained adjustments. So there's a little wiggle room here. Batch sizes between like 64 and 256 are fairly common. The number of epochs is how many times you look at each individual image. So with 5 epochs and 128 images, I look at batches of 128 images sequentially in my training data until I've looked at all 60,000 of them. And then I'll repeat that process 5 times. So I'll look at all the training data, then I'll look at it all again, and the number of epochs is how many times to look at the entire training data set.
Before the back, what do you call that,
Back propagation?
before back propagation happens, or
No.
128 and then back propagation, 128 then back propagation? So you do 60,000 of them and then you do it the entire cycle 5 times.
Yes, the second thing.
And okay, because the first entire round, the sprint, it's trained to a certain extent, but now you rerun the data, it's going to be even more trained.
Exactly.
Interesting. Even 5 times.
Yeah, and you might, in a really complex situation where your neural network is really, 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 really big, you might need more epochs. So often, like to put this in perspective, we talked about AlphaGo. Okay, AlphaGo, when it did the show match against Lee Sedol, the Go champion, it trained on a Google supercomputer for 1 month. Not 1 month of CPU time, 1 month of wall clock time, constantly training, which is, on a Google supercomputer. It's insanity. So some of these models, the number of epochs is huge. And this is also where, Brian, you mentioned overfitting. This is also where you can get yourself into trouble on overfitting. If you need to train for many, many, many epochs, then you're seeing each individual training sample many, many, many times, and you definitely have the power to overfit to kind of memorize the training data.
Gotcha. Yeah, that makes sense.
Okay, verbosity is, verbosity is just for the output. And then you can specify how much of your training data to leave out as validation data. So in this case, I've done 10%. Let's do 20%. I think it's just better. Okay, and then we'll run our model, and you can see it training live right now here. Boom, boom, boom.
What is validation split again?
It's how much of your data to leave out of the training process to use as a form of like mini test data, right? So 20% of our data will never be used to train the model, but it'll be used as a proxy for how well the model's going to generalize.
Got it. Because you're basically talking about you want to split it down, so the network has to be gone down. So that's the 20% going down. Is that what?
No, a little different. So with validation split, we've got 60,000 total images. We're going to take 20% of that, and we're going to hide it from the network while we train the data. So we're going to do a single epoch with all of this data. It'll train, and then we will run the data through, run this 20% through without doing any back propagation. We won't train the network on this data, but we will run the data to get its predictions and find out how accurate it was. And that's to say, we want to know how well the network does on data that it's never seen before as a way to tell if we're overfitting or not. Because it's definitely possible to essentially just have the model memorize.
Exactly. And then what's the point?
Exactly. If it can only work on the data that it's seen, then it's not a predictive model at all. It's useless to us.
Yes.
It's kind of interesting that the overfit between train and validation is also decreasing with each epoch.
Yeah, this network did really well. Let's look at a little visualization of what we just did. Because you can read the text here and that's all well and good, but we all know from real world data analysis, you don't just look at the Excel spreadsheet and then do like some savant shit in your brain. You chart the data. So if we run this chart, basically, what are you talking about? Oh yeah, accuracy. This is a problem of different versions of Keras. So an older version of Keras used ACC. Now they want you to spell out the full word, accuracy. I'll update this so it works. Okay, so here's how well our model did over time on the training data in the blue line and validation data on the orange line. This right here, you do not often see. So, bask in the glory of the fact that we're actually doing better on our validation data. We're making more accurate predictions on the data we've never seen than on the data that we have seen. That's pretty cool. And it will not always be your experience in the world of deep learning, I promise.
So when does the validation cycle run? The training cycle has 5 epochs. Then when is the validation happening after each epoch?
Yes, at the end of each epoch.
And at the end. So okay.
Right. So the
Okay.
training data goes through. You do all the relevant backpropagation for that training data.
Right.
Then
Right.
once that's happened, the last section of the epoch is to evaluate the validation data.
Right. So when it evaluates it, it also adjusts our parameters to determine if they were right or wrong, and then adjust that onto the validation step as well.
No, not during the validation step, only during the training step.
So what is validation? Validation is just feedback how well we are. That's it.
Exactly, exactly. Feedback for us, how well's the model doing?
Got it. Not, it doesn't affect the model or training.
That's correct.
Okay. So yeah, so we're basically saying, okay, after 5 iterations, we were pretty good. And if you maybe increase the epochs, or maybe we'll get slightly better, right?
Yeah, it might get slightly better. In fact, we can try. So let's unclick annotate. So one thing to say, if I just rerun these 2 lines of code, this model will be starting from the place where I previously trained it. This went really fast, so I want to see the entire chart. So I'm going to recreate the model by rerunning that again. And then let's go 10 epochs, double the training time.
Mm-hmm.
Zoom, zoom, zoom. Okay, and you can start to see, this is a really simple model. You can start to see how the training process might be annoyingly long with really complex models with tons of parameters.
Mm-hmm.
Okay, rerun this. And we see still a really nice, smooth convergence curve, really close, tight performance. You know, if we were looking for overfitting, what we'd want to see is these lines eventually might cross. And especially if you start to see something like this line starts to go down, this is overfitting.
Mm-hmm.
And same thing, usually, often, maybe not usually, but often, the training data, you know, this position of these 2 lines will be inverted, where you're often doing worse on the validation data, even from the very beginning, than you do on the training data. So if you saw a chart like this one, so orange is our validation, you know, this is actually pretty common to see. You'll see validation do something crappy like that, and you'll see training just like keep on getting better, and, you know, you go, okay, well, that's not good. We have weird eyes and a frowny face. Okay.
Mm-hmm. Yeah.
Clear that bad boy out. And, you know, we can ask ourselves how our network did. It did pretty good. 90% on the test accuracy. It's not bad. The best models, this is pretty much a solved problem now with modern convolutional neural networks. You can get like 99.98% accuracy, which is incredible, absolutely amazing. But for, you know, 10 rounds of training, it only took us, what, like 40 seconds maybe to train this thing. It took us like 3 lines of code to create the model. And we have good reason to believe that our results hold. You know, we got about the same score on our validation accuracy as we did on our final ultimate totally left out test accuracy. We have no real evidence of overfitting here. Our training data and validation data grow in the same direction pretty consistently. The loss function is a really nice stable curve. There's no jittery spikiness to it. So I think we did pretty well. We tried training it for more epochs and it got a little better, but you can see the slope of the curve is kind of really slowing down. That means, you know, we might be able to train this thing for 20 epochs and get a little bit higher score, but maybe not. And we could try it, right? And just see empirically if it works. But it's slowing down. So if we want to get steep curves up past 90%, we might need to experiment with the model and give it some more parameters or give it some more layers or, you know, give it something else to work with rather than just more training data.
So we never established how many hidden layers it's going to have, right?
We did. It's only got 1 hidden layer, and we did that up here in this part of the code.
I thought that was the hidden, the input layer. That's what I assumed.
The input layer is implied by this input shape. So we created the model. There's an implied input layer kind of here. That's our actual image is 784.
Okay.
implied by this. And this dense layer, this one with 32 nodes in it, is the hidden layer.
There. Okay. Okay.
And then this one's the
Output.
other visible layer, the output layer.
Okay. Okay.
Okay.
So one layer.
Yeah, just a one layer network. And down here, there's some, adorable code for plotting specific specific examples and how our model did. So look, this one is the only one we got wrong in that particular example. We called it a 6, but it's actually a 5.
Mm-hmm.
It got confused by this little round bulb, probably.
Mm-hmm.
Let's look at another page of 16. Okay, interesting. It called this one a 6, but it's actually a 3. That's pretty bad. That's not a 6. Should have guessed 8. Dumbass. Stupid machine. Okay, that's a 4. And this is what I mean when these are hard. I guess if you knew that you could only choose digits, 4 is the same thing to choose, but that's an upside down pi symbol. That's not even.
Yeah, this is not a 4. Stupid human this time.
Yeah, exactly. Which is always a problem. Okay. And then, the challenging thing is to do a little better. Okay. So there is an exercise now that I'd like to challenge you to do in your own little Google Colab environments while I'm here to offer support and guidance. So if you go to this repository and you click on the practice exercise, I'm going to challenge you to build some specific neural networks that do some really specific things and answer some questions about them. If you look at the third, okay, so let's keep this up and go back here. If you open the third Python notebook in Google Colab or wherever you're working, there are some more examples and some helpful code. So you might want to just copy this top one to get you started. This function is a training function, or is the plotting function that creates these curves. And there's also lots of examples of me doing things that are very close to what I'm challenging you to do in the exercise. So lots of different examples, training for a long time, making a small neural network, making a larger single layer neural network, making, I think here's the first multi-layer neural network, right? And you just add 2 more layers with tons of parameters, right? So this is all just good examples that you can reference while attempting this exercise. Both of you feel comfortable and like you want to do that?
Yes.
Booyah. Okay, let's start.
Can you, so it's the same repo. There's only one repo we were talking about, right?
Correct.
Okay. And this one is four practice exercise in one.
Yes.
1.4. Okay.
Okay, I'm gonna freshen up my coffee real quick again. This time I don't have to make new coffee, so it'll take like.
Can you run this code in Google Code Notebook as well?
In
Both are
Collab,
run?
yeah, you should be able to.
Okay.
So let's go Collab. I'll go GitHub. Yeah. Lab, deep learning, and then I'll open this third one here.
It has a run feature.
Yeah, and you can run any of the code buckets if you're focused on them. If you do Shift Enter, it'll automatically run them, so you don't have to use your mouse so much.
Nice.
Oh boy, but that's not fun.
Yeah, I ran into that problem even just running in Jupyter. I had to go and install TensorFlow,
Ugh.
which worked really simply with just with a pip install. I've heard it was really difficult to install, but it actually went really well. That's needed.
So to fix it on Collab, they're telling me to use tf.keras. So I wonder if I go Spotlight, import keras as, whoops, import Okay, it seemed like that still ran just fine. What about you? No. What if I get TensorFlow as TF? Go TF dot TF dot. Oh, this is gonna be so annoying. Then the other thing is tensorflow.keras. And I won't need this. And if I spelled it right, that would help. TensorFlow, 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 TensorFlow. Now what say you? This looks like it's working. Okay, I gotta make a note for myself here. On Collab. So I guess it's time for me to upgrade all this to Keras or TensorFlow 2 and use Keras. Okay, so Aziz, did you catch that fix?
Partially. If you can put it in the chat, I was actually reading as well while you were doing it.
Yeah,
So,
basically, I just changed all the imports to, they used to say just plain Keras, and I
so
changed them to import tensorflow.keras. This is because recently
yeah.
TensorFlow and Keras kind of merged. So they used
Oh,
to be separate libraries, but now they're the same.
okay. Okay, so the exercise, part 1. It seems like the solution would be just 3 or 4 lines of code to create a model, create the input layer, output layer, and answer the questions. Correct? Is that the intention
Yeah.
of part?
Yeah,
Okay.
absolutely.
Okay. So it's not really I mean, the output would just, okay, so, okay. Yeah, I'll just do one thing at a time.
Tyler, can you hear me?
Yes, what's up?
The mnist data, when you load it, is that loaded into a ND array and NumPy, or is it loaded in as a data? It's not loaded in as a data frame, right? It's loaded in as a NumPy ND array.
Yeah, I'm pretty sure it's a NumPy ND array.
Okay, just which with each being one.
Each one is one image, yeah. So the shape is like 60,000 by 28 by 28.
Gotcha. I was just trying to picture data prep in my head, so that makes sense.
Cool.
But yeah, I'm good.
By the way, let me know when you've got your first, neural network training.
300,000 trainable parameters.
So when you say make 300,000 training parameters, how is a training parameter determined?
Perfect. Okay, so every weight and every bias is one of our trainable parameters. And you can call on your model, you can call this function model.summary to print out how many parameters there are. Sometimes certain kinds of layers have non-trainable parameters, and you can also freeze layers, so you can make parameters that would have been trainable, non-trainable. But in the dense layers, they're all trainable by default. So this one here has 25,000 parameters, and we did the math, but we can do it again real quick. The idea here is the input layer is 784 pixels times 32, because each one of those pixels has a connection to each one of these hidden layer nodes. So that's the number of weights in the connections from the first layer to the second layer, plus each one of these 32 nodes has a bias. So this is the first layer has that many trainable parameters. And then the second layer has from 32 nodes to 10 nodes for the weights, plus 10 biases. And so if you do that computation, it ends up being 25,450.
Okay, so image size times units plus 32 plus units, and then units time the end output plus the bias. So actually the math is the same. It's just, got it.
Exactly. And you don't have to do the math, right? You can just call this summary function. And
Yeah.
so, you know, if I want more, I can just go like, let's see what it's at 1,000. Okay, 1,000, that gets me enough.
Okay, so I think I have the base code. However, I think I will need, on the third one, I will have to copy all that code to have that preparation of the data, right?
You mean part 3, or you mean just training
No.
this?
No, so I'm on part 1, and
Okay, yeah.
I am, I already, I wrote the model part, but it's giving me an error. I think I will need to copy certain code. The error is session line number was not unique in database history logs moving in the new session 60.
Oh, that's wild. Share your screen.
Let's see how to do that. I think you'll have to, oh, I see it, share.
In the when you call dense and when you're adding the hidden layer and you put the input shape being image size, you're doing just one hidden layer. Do you need to put it in that like tuple with a single number format?
Oh, you know what? I'm not sure if you might be able to just specify the number and it'll figure it out. You should try it.
All right.
Okay, you got that. Error, session line number.
Object is not iterable. Yeah, you need to have it.
That's a strange error. Int object is not iterable. Oh, yeah, so this is the same error that Brian's just describing. On input shape, following that 5, add a comma.
Oh, really?
So this is the difference between, in NumPy land, this is the difference between something that is just a 5 versus is a vector of 5 things.
Okay.
So I think another way to say that is it's the difference of a single array with 5 items in it and an array with an array that has 5 items in it.
Cool. So now the goal is to get this to 300,000.
Yeah, at least. And you can do it either by adding layers or adding units to your hidden layer, either.
Okay, cool. I'll stop sharing.
I'll share this great image. Why not?
So in part one, we are not considering what kind of data we are going to get, right? So we don't care about that, correct?
We're still just using mnist. Yeah. Maybe I don't understand the question.
So when you determined input shape, input shape in the number of size. So when I'm doing part one, I'm not considering what kind of data I'm going to get. Meaning, am I going to get an image? Am I going to get this kind of image? That kind of image? We don't care.
Oh, no, you should assume that you're using the same 28 by 28 images that I was using here, the mnist data.
Okay.
Which means your input shape, actually, I totally should have caught this because you have your input shape as like 5. Your input shape should also be 784 because you're going to be using the mnist.
So where am I getting that code from? From the third exercise for that sample list?
You can get it, yeah, either from, so here, this does it all at once. If you just grab this block of code, except of course you'll have to, here we go. I updated the imports to work here. If you grab this code, and I would grab this function too, because it's just helpful for plotting. This will load the data, reshape the images to be the flat vectors, and then produce the one hot encoded vectors here. So this is in the third.
Third, right.
I think I'm about ready to train.
Oh yeah.
Batch size, should we just keep it at 128 for now and play with that after our first kind of iteration?
Sure, or do 64 or do 100 or, whatever floats your goat. Share your screen, I want to see it train. We'll celebrate together.
Precision. There's no precision metric.
Oh yeah, you might have to implement it from scratch.
I'm not worried about it right now.
I have somewhere, I have done that.
Oh, I think I know what it is. When you're doing a single layer model, your activation needs to be softmax in your unit, right?
Yes, in your final layer, it definitely has to be softmax.
But if it's a single layer,
You'll need to always add at least 2 layers explicitly, the first hidden layer and the output layer.
oh, okay. Gotcha. That was.
And by the way, in the third, sorry, not third, in the 8th notebook series, ML product lifecycle, in the second notebook, I'll send a little link here. Near the bottom, there is an implementation of precision recall and F1. You can do these custom. I'll send the code also to chat. So you can take a look at that code. It's a little bit confusing, but it is an implementation of recall precision and F1 score. And then when you use them, you can just add them to the metrics by name rather than by the string of the name, since they're not built in by the name of the function. So again, it might be a little more than you want to do right now, but it would be nice to try later.
All right.
Oh, nice. And it kicked ass, 94%.
With just a little bit of overfit. Pretty good.
Yeah, negligible overfitting really though, like 0.5%, that's still. Scroll up, I want to see what's the shape of this thing?
I went for the exact approach. 300,000 exact.
Nice. Sweet. And now notice, right, that since you didn't redefine the model, look at your accuracy on that first epoch already at 95, right?
Oh, okay.
So you started from the point where your previous training session left off, and now you trained 10 more epochs. So now you've actually trained for 20 epochs.
Oh, okay.
But the first 10 had a batch size of whatever it was, 128, and the second 10 had a batch size of 256.
Okay.
And,
Interesting.
yeah, and so you can use this strategy. This is actually, we talked about transfer learning. It's actually kind of common in certain cases to adjust your training as you go. So, sometimes you'll want a really high learning rate right at first, and then you want to taper your learning rate off for gradient descent. So you learn slower as time goes on. With transfer learning, you want to actually train only parts of the network at once. So you'll like run several epochs where only the final layers are actually getting updated. And then you'll unfreeze some more layers and train those, and then unfreeze some more layers and train those. So there's lots of interesting things you can do during the training process that you can also be engineering that.
Interesting. So how would you kind of, like you said, unfreeze layers without redefining the model?
There are functions in Keras to grab individual layers, and then there's a parameter on each layer. Each layer is like an object, and you can say basically equals frozen.
Okay.
Let's see, I have some examples of that code somewhere.
Would you call that in the fit function, or would you do that separately before you fit the model?
You have to do it, basically, if you wanted to do it in parts, you'd have to have a loop that goes like, set the frozen, call compile, fit, then unfreeze or freeze some more, then compile, then fit. So at compile time, when you call model.compile, that's when it recognizes and kind of fixes the frozen values.
Oh, okay. So you'd have some sort of for range 100, and then you need some subset of that, right?
Sorry,
Or
you broke up there. Could you say it again?
break up and iterating through this times, but only doing a subset of the model each time.
Oh, yeah. Okay, so let me send the code to chat. This code here that I just sent it to chat, for layer in model.layers, and then freeze first n layers is some number, the number of layers you'd want to freeze. You just go layer.trainable equals false. And so then you'd put this little code on top of your model.compile to freeze whatever number of layers you wanted to freeze each time. And then you'd call compile just like you're doing, and then you'd call fit just like you're doing.
Okay.
Aziz, I think you might have said something, but I didn't hear it.
No, I didn't say anything. But I don't know. I completed it. It works.
Show me.
And I played around with the numbers.
Okay,
So,
awesome.
yeah, so I just basically copied your code here, and this is really my code.
Yeah.
Went to 300,000, and then when it was 10% validation, then it was 94. It was pretty good. The chart was, but I changed to 30%, and now I'm getting 93 point something percent. And
Okay, yeah, that's interesting. Not entirely surprising. You're holding out more data, so your model is getting a little bit less to train on. You're also holding out more data, which means you might have a more representative validation set. So you might be getting more signal this way. It might have been the case that your model with only 10% validation was actually worse, and you just didn't know it because it was good on that 10% of the data, but it's worse on that 30% of the data.
So, and every time we run it, given the same parameters, our results should be exactly the same, correct?
No, only if you fix the random seed, because some of the training process, especially the creation of the initial weights, is random. So if you pick a random seed at the top of your file, and then
Right.
you run all the code starting from that random seed, then you'll get deterministic results. But if you just rerun the code without setting the random seed, very probably you will not get identical results.
Okay. Cool. So I have a question on your question.
Okay.
So I understand this part. How many weights and how many biases? So how do I know the number? I don't know how to determine the answer to that.
Okay. So the number of biases is always going to be equal to the number of nodes you have total in your network, at least when you're just using all these dense layers. So you have 378 biases in that first layer, and you have 10 biases in the second layer. So 200 or 388 biases in total, and then you can subtract that from the total number in summary to get the number of weights. All the other parameters that aren't biases will be weights.
Okay.
Does that make sense?
Yeah, no, not completely. I'm processing it. So weights, I understand. Those are okay. Okay, so biases means these are the hard outputs. We know them for sure. For sure, these are the outputs. So these are like, we are biased that this is an 8 and it is an 8 and it's an 8, and this one I don't understand why these are biases, and I understand the weights. So So am I on the same page with you?
Not quite. Let me show you this picture from the first notebook we did.
Yeah.
Okay, so the weights are the things that modify the incoming input values, and
Right.
each node has a value called a bias that gets added to its sum function irrespective of the weights that get added in. So
Bias is the node which gets added from the previous layer.
the weights modify the values coming in from the previous layer. The
Right.
bias is specific to each individual node. So every node has one value called a bias that gets added to the sum of the weighted inputs.
Right. Okay, so this green circle is a node.
Yes.
Okay, so a node has a bias which gets summed from which is used with all the weights, and that goes into the algorithm which determine a new bias, or a new weight. Sorry.
A new output, which will then be modified by a weight. So on all of these output lines, one sec. So all of these output lines are going to be multiplied by another weight before they go into whatever respective node they're going to go into.
Got it.
And each of those nodes will also have, a bias inside of it.
Okay.
So if we scroll up here, actually.
So if each of the nodes are going to have a bias, then why aren't the number of biases 300,000 for me? But you said no, you have 388 biases.
Yes. Okay. Share me your screen again.
Okay.
So that first layer, model.add units equals 378, that says, make me a layer with 378 nodes.
Right.
Each of those nodes has exactly one bias.
Right.
So that's 378 biases.
Right. Yes.
Now your next layer says 10 more units, which means 10 more nodes, which means 10 more biases. So we can just add those two numbers up to get the total number of biases throughout your network.
Got it. Sure, because it's only 3 layers for us. One is the initial layer, one is the last layer, and one is the middle hidden layer.
Exactly.
In this case, it's a simple math. So, but parameters is the trainable parameters.
It's the sum of the weights and the biases.
Weights.
And so the weights explode. The weights, you have way more weights than you have biases because you have one bias per node, but you have one weight per edge in your graph, basically.
Right. Okay, got it. Okay, so those are all of them. Those weights are between the layer. The weights are between the layers, correct?
Yes.
Okay, and that is kind of generated based on our inputs and based on the number of layers we have.
Exactly. So in your case, to get to
Algorithm.
300,000, you go 784 times 378. That's the
Input.
number of weights in between the first two layers.
Right. 378 is not the number of, not the inputs. Inputs are 378. Got it. Yes. Okay. All right. It's new world for me. So.
Yeah, stretching your brain, I can tell.
Okay. Cool. Thank you.
Yeah.
I tried that again with 1,000 layers and got some pretty bad overfit.
Yeah, I bet you did with 1,000 layers. Show me.
Wow.
Worse than guessing randomly. Oh no, not worse. Wait.
Oh, it's 30%.
No, what you're showing me is actually pretty good.
It's 93% accuracy.
Yeah, that's good. Not terrible.
Right.
That has 1,000 layers? Are you sure you're looking at the 1,000 layer one?
Make sure. I'm pretty sure I renamed it all model 1000, history 1000.
Oh, so you wrote a loop to add the layers, right?
No, I just created a new model with 1,000.
1,000 nodes.
Sorry, 1,000 nodes, not 1,000 layers.
Okay.
I'm sorry. That's
nodes.
no, my bad. Yes, 1,000 nodes.
So instead of the unit, when you say nodes, those are the units, right?
Correct.
Okay. Yeah.
Okay, yeah, and so it probably took a little longer, 2 seconds to train per thing. Still 93% accurate. That's not terrible.
Compared to a second.
But you had like 96 on the smaller model, right?
No, I got it to. Oh, when I did it for 20 epochs.
Oh, yeah. Okay. Yeah, and so more nodes doesn't always map cleanly to better performance. That's one thing that we always have to be a little bit aware of.
Okay. So when you say how different was the model's performance on training data, I understand that. But when you say test data, you mean the validation data, correct?
There's three kinds of data: training, test, and validation.
Okay, so what's
So the validation data happens when you do that validation split, and it's
Right.
some subset of the overall training data.
Right.
There is additional data that Keras provides for us, which is test data, slightly different from training data. Let me see, where am I at? This one probably has it. Oh no, where was I? Here we go. Okay. So when you import the data, you train it on the training data and the training labels, and the validation data comes from this subset of the data. There's 10,000 test images that they give you separately with separate test labels. And during the training process, even during the validation data process, this isn't used. So later, if you want to evaluate your code, you use the test data. And the reason for using test data this way is like the validation data biases us. We try to improve the score on the validation data. So typically you wouldn't actually use the test data until you have like 2 or 3 models that you're really happy with, and you think any of them could go to production based on their validation scores.
Mm-hmm.
And then you look at the test data, which you've never seen before, your models have never seen it before, it's been totally left out, so you couldn't possibly have incorporated any information about it into your training process.
Mm-hmm.
And you use this model.evaluate
Yeah.
function to see how it did there.
Okay. We didn't look at that code, did we?
We didn't talk about it explicitly. I kind of breezed over it, but this is in the second notebook. And actually in the third notebook, this plot training history function, it actually calls that evaluate method in it and prints out the test loss and test accuracy. But we absolutely did not talk explicitly about it today.
Mm-hmm.
Make sense? Feel good?
Yeah, I do.
Me too. One sec.
How long did each epoch take? How would we know that?
I think it's just from the printout when you run. So if you run the model fit without running the plot, it'll give you the
verbose. If I do verbose true, I'll probably see it, right?
Yeah, verbose needs to be true. Although if you don't call it by itself without another, since you have the plot function after it, it may not print it.
No, it's printing for me. I have the plot function after, and I did verbose true, and it's printing it for me.
Okay, I wasn't sure. Sometimes it gets skipped over if it's not the last print, but I wasn't sure how verbose.
Wow. Okay. Interesting world.
Why am I in this one?
Okay, so in part 2, you're saying create 3 networks. When you say networks, you mean models?
Yes, that's exactly right.
Okay. And they're going to be independent. They don't, of course, they don't talk to each other. It's just us kind of figuring it out.
Exactly.
Okay.
For part 2, are you, and once you make the 3 models, for the first one, are you implying that we should grow, expand or contract the nodes per layer consistently, or
what I mean is you should choose a number between 10 and 50 and make one network with that many of nodes per layer, but have it be consistent. I mean, you can jump around if you want. You will find that the results are remarkably similar in this particular case. But my intent was just to say, pick some number between 10 and 50 and have 10 hidden layers that all have that same number of nodes.
Okay. when we're setting up our models, when we call the different hidden layers, is it only the first hidden layer that needs the input shape definition?
Yes, and in fact, if you try to specify an input shape on other hidden layers besides the first one, I think you'll usually get an error. And basically what Keras is doing is, since it knows what the size of each of the input layers are as you're creating it, it just infers the size of the input to the subsequent layers based on the size of the previous layer.
Can you repeat that sentence?
Yeah, so when you create something with Keras, you know, you're saying like first do 10 layers. So on the first layer you say like, hey, there's some hidden input layer. It's weird to say hidden there. There's some input layer that I don't explicitly specify. So on the first layer I say input shape equals whatever.
Yeah.
Based on, you know, I happen to know that this is 784.
Right.
But I also say this thing has 32 nodes using units. Then when I'm adding the second layer, I say, let's have this one have 37 nodes, just so it's different than 32. Keras already knows that the input shape for this layer, the 37 node layer, is going to be 32
Right.
because you add them, you know, sequentially.
Right. Okay.
Can I share my screen real quick, Tyler?
Yeah, please.
So I was trying to write a function just to create number of layers, number of nodes, so I could do this really fast.
Brilliant.
Does that look right for the model summary and how it should look for a 10-layer model with 5 nodes in each layer with the parameter numbers?
Yeah, 1, 2, 3, 4, 5, 6. Yeah, absolutely.
Okay.
Right, and since you only got 5 layers, your number of parameters overall is quite small because you're just getting 5 times 5 is 25 weights in between each of those 5 by 5 layers,
Okay.
and then 5 biases, so 30.
Okay. And the fact that I'm using just model in this function, since I've already called that earlier, is that why I'm getting dense numbers that are 13, 14, 15, 16 and not starting at 1 again?
Yes, and for every session, you know, every time during a single like in-memory session of Keras running something, it'll increment that. So if you run that function again, you know, next time you'll get 23, 24, 25, 26, 27, 28, 29.
That's not going to matter with reference to running the model. Like after when I compile it, it's not going to pull in those other layers from the previous model, right?
Correct, they'll be separate.
Thanks.
So you also mentioned that when you kind of rerun the same code, the model is the same, and we'll actually retrain, or not retrain, but add the additional training. So how do you kind of reset it?
If you recreate, so if you do like model equals sequential, every time you call that, model's going to now refer to a new instance. But if you gave model equals sequential, add, fit, model.fit, and then call model.fit, then you're referring to the same model. So to reset it, you just create a new model and replace, you know, the value that's in that variable. Does that make sense?
Yeah, it makes sense. I feel that I did that, and I'm just seeing. Yeah, the results are correct. Okay, as expected. Okay, good. This is fine.
Sweet.
Can you prove when you call sequential? Can you provide a name?
I think that you can. Keras, give model a name. And I think you can also provide a name when you're creating individual layers.
Oh, okay.
Okay, I found a Stack Overflow on this.
I'm trying to find it in the docs, but it's
It's pretty easy. Instead of adding it when you're calling sequential, after you call sequential, you say model equals sequential, then you go model.name equals, and then set whatever the name you want.
oh, okay.
But then in the layers themselves, you can add a keyword parameter called name. So units equals 32, input shape equals whatever, name equals the name you want to use.
Okay.
And in fact, I'm making a video of this, so I'm going to share my screen and just show what I was talking about on the screen so that people who see this later who don't have access to chat. To you viewers at home,
So what does the name help you do? So model the name to refer. How does that help?
it doesn't help much. It's only for like debugging purposes. But instead of seeing in the summary like dense 32, dense 33, dense 34, dense 35, you could set it to be some explicit name. And this can be useful when you're talking about like, right now we're kind of building toy small architectures.
Yeah.
When you have a really big architecture like MobileNet or Exception, each little block, each layer might have some kind of important meaning, and you might want to track it by a more meaningful name.
Right. Okay. Okay, interesting. So in part two, when let's say you're saying the first model has fewer than 10 nodes per layer. And when I made the first layer, I said, okay, 9 units is 9, right? But then when I'm making my for loop and actually adding the hidden layers,
Mm-hmm.
the 9 is going to grow potentially, right? The nodes are going to grow, or should I be defining?
You should be specifying that. So share your screen.
Yeah, okay. So when you create your hidden, I'm doing that. When you create your hidden rows, hidden layers, in every layer, you control how many nodes each of them are going to have.
That's exactly right.
So I did this.
Right. Yeah. Okay. So each time through this for loop, you're just setting units to 9. So it'll always be 9 nodes in each layer.
Right. Where's my first one? So 9, 30. Over here, I'm going to say 30. And over here, I'm going to do 70 to apply the exercise. Okay.
Right.
Right. Oh, this one.
Those are all still right because you're still making a prediction about whether it's a 0 through a 9.
All right. Let's see it.
Training. I did you with my bits.
Oh, wow. Training. What is that?
Awful.
Yeah, so this one is the first one, right?
Mhm.
So when we have very little, I mean, these are just assumptions, right? So this is the first one, which has 10 nodes, 9 nodes, and a lot of layers. So training becomes worse.
So
Pretty
yeah, so
bad.
that's the loss, and the accuracy was also pretty bad.
Okay, yeah, it's very bad. And this is the second one. So this one's better.
Oh, interesting. It did a lot better.
And this was 30 nodes and
And still 10 layers.
same 10 layers, right? And this one looks better. It's 90, slightly better. So this was 70. So not much gain.
Hmm. I'm
But
actually a little surprised that those bottom two did well. Scroll up. I want to see your code again.
the epochs have to be 10.
It could be anything, but I asked for 10, yeah.
Okay.
Oh, interesting.
This is an interesting world. And then I have after you have your comment on that, I have a question.
I know what's going wrong. I know why I'm not seeing what I expect. Look in your second two for loops. Which model are you adding units to?
Oh.
Okay, good. Now all three of your models should suck. That's what I'm expecting to see.
Okay. Okay. So this one sucks really bad.
Good, sucky. Brian, are you also to this point where you have three shitty models?
I'm about to be.
This is as bad. It's not any better.
Yeah.
2.3, 13. 2.3, 13. So this is 11%, or is it
Yeah.
0.1%?
No, 11%.
It's 11%. Okay.
Which means it's 1 percentage point better than guessing.
So they're all similar. Interesting. Why?
Okay. There is a problem called the vanishing gradient problem that you're experiencing here with the sigmoid activation function. So what's happening here is as we add more layers, now you've got the whiteboard, okay. So as we add more layers, the way the gradients work for backpropagation, like I said, is calculus. It's the chain rule. So let's say we've got 10 layers here, okay? 1, 2, 3, 4, 5, 6, whatever. Let's just say we have 6. I don't want to draw 10. The activation function we're using is this function, the sigmoid function. The derivative of the sigmoid function, the slope of this line, if I had drawn like an actually good line, it might make more sense. So let me try and actually do it. Zoop. The slope of this line is never more than 0.2. Okay, that's just a fact about the default sigmoid function that we're using here. So the value of the gradient when we compute our error, we have our predictions on this last layer and we have our true values. We compute the difference between these, and then we use the derivative of the activation function to propagate back that error. But since the activation function can never have a gradient of greater than 0.2, because that's the slope of this sigmoid, then this first thing is going to produce a value pretty much between 0 and 0.2. And then at this second layer, because of the chain rule, this gradient is a multiplicative situation. So this is going to be 0.2 times 0.2, which is going to be like 0.04. And then you're going to have something back here, 0.008. So this value controls the magnitude of the adjustments you make at every possible layer. So the weights and biases in these early layers are only ever adjusted by tiny amounts. And that has to do with the activation function that we chose. So for a while, for a long time, like, okay, so I didn't tell you this, but the first neural network was actually invented in the 1940s. This was hypothesized, and we didn't have the computational resources to really make them work. And especially we didn't have the computational resources to, do these really deep layers. So later when we started being able to do more deep layers, we figured out this problem called the vanishing gradient problem, where we had been using the sigmoid function because it's cute and it kind of models activation and it had some nice properties, but we learned that it has this problem. So we invented a solution to this called the Rayleigh, which I mentioned earlier, rectified linear unit, where it's a 0 below 0, and it's just a flat line with slope 1 above 0. So this has its own problems because you can get some dead nodes that, once their activation is down here, they just don't change anymore. But when they're up here, instead of having, 0.2 times 0.2 and cascading that decimal growing smaller and smaller and smaller, you just have magnitude 1, magnitude 1, magnitude 1, magnitude 1. So the gradients can actually propagate backwards this way and still maintain large magnitude. Okay, so if you go to your code now and change sigmoid in those loops to Rayleigh, R-E-L-U, you'll get different results. Yeah.
Even the first one, right?
Yep. Except for the final layers. Final layer should still be softmax.
Right. All right.
And actually, I should have just, instead of trying to draw a crappy Rayleigh, I should have just shown you the actual, I have it.
Yeah, now it's better.
Okay, so now here's the actual Rayleigh line is in blue, and here's the derivative of Rayleigh. It gets slightly above 0.2, like 0.21. You want to show your results now, Aziz?
It's getting processed. Mine got 89%, and the others are getting processed right now.
Sweet.
Oh, we're done now. So
Look at that.
So the more you do it, 95 and then 94 and 89, 88. 88.
And that's not that surprising with, many layers, but they're all really small. You still kind of have a hard time learning complex representations. You do well, about 90%. But as you add more nodes, you get a little better, you get a little better.
Mm-hmm. So in theory, you should get, not really, but generally to a certain extent, you should get better over more layers, but then you're going to have overtraining.
Yes, you do start to put yourself at risk for overtraining. And you do see like kind of a little bit of that in this last chart here, right? The validation loss kind of creaks up at the end there. Let's look at the accuracy too. Scroll up just a little. You see the same thing, but you see the same little, it flips here. Yeah. It's still relatively close, so I wouldn't say you're crazy overfitting, but it is 97 versus 96%, it looks like. So a full percentage point of difference.
96 and 95. So it's, yeah, almost a percentage.
Yeah, and like you were saying, generally speaking, you should expect as you add more layers and as you add more nodes to each layer, generally things get better until you get to the point where you start overfitting it.
Okay. What do you mean by, I actually don't understand, what do you mean by the loss, the test loss or the loss?
So loss is the value of that function categorical cross entropy over time. So that's the data that's actually being used to back propagate and adjust your scores. So it's the metric that we've chosen to use, and we've chosen to use it because it's an established good function to use, categorical cross entropy, for these kinds of problems. But so you can see, the accuracy actually tells us something about how often our thing is guessing correctly. The loss value is kind of hard to interpret, but it's really, really meaningful to the machine. It's the only thing that the machine is using to adjust the weights and biases is the value of this loss score.
Okay, okay. So just the way accuracy is humanly explainable, loss is not really explainable, but it's
or at least it's harder to explain and harder to interpret.
okay.
But you still look at it, you know, the same way you look at both of these curves. You go, what I want to see is a pretty smooth slope converging towards some value. If you see like lots of spikiness, that's a sign that things are going really wacky in your training process and that you're probably not, you know, you're not slowly getting towards a good solution. You're changing your weights and then the scores change dramatically, and then you're changing the weights a little bit and they change dramatically again. That's not a good sign, so you don't want spikiness. And you also ideally want these two values, your validation and your test scores, to be pretty close together. If you start to see them wildly diverge in either direction, that's a sign that you're overfitting or that something else is going wrong.
Right.
So the way to improve these models was to switch the Rayleigh activation.
Yes, that should improve them.
I got pretty similar horrible model accuracies.
Similarly horrible, huh? Okay, show me your screen.
So the three of them, I did 10 layers each, 5, 25, and 75 nodes.
Okay, and show me that function real quick.
It's right here.
I see sigmoid.
Yeah, so these are the sigmoid ones.
Oh, okay.
I haven't run the Rayleigh ones yet.
Oh, got it.
But yeah, about a second to run each, and then accuracies in the 0.1.
Exactly. Yep. And this is, you know, again, the vanishing gradient problem. It's just like with the sigmoid function, there's a pretty hard upper limit on how many layers you can have and actually expect the error values to propagate backwards meaningfully through the network. They just get vanishingly small, and then you can't learn anything.
So,
And then really as a result of adding Rayleigh to part 2, you've all solved part 3. Found something more than 92. Aziz, you had all the way up to almost 96% test accuracy.
so yeah, my first one, the 5 node, the 5 node up to 134.
Oh, that's still not great, but yeah, 5 nodes, that's a very thin layer. Hard to pack representations of data into that.
Yeah, just jumping to the 25 node, it jumped up to 92, 93 with a little
Tiny bit of overfitting maybe.
and then 75.
Definitely more overfitting.
And quickly.
But you know, you'll note like your validation accuracy is still quite high.
And then we're at 95.
And test is right in line with your validation scores. So, you know, if you saw that gulf getting bigger and bigger, you'd expect your test data to go down. But at that level of closeness, you know, that's still a model that, you know, is a candidate for production, I would say.
Got it.
Okay, boom. So we've completed the exercise. We've done the lesson. You can review this this third notebook if you want to just see a little more discussion of things that I've done. And, you know, you can see like some of this is the spikiness that I was talking about that you don't really want to see. This is a single layer with just 5 units. It still kind of smooths out. It's not terrible, but the fact that these jump really big for small adjustments is not a good sign. Similarly here, spikiness and terrible accuracy, not a good sign. And you can kind of just look through here. Here's really big overfitting, right? 4% gulf, and it happens after the first epoch. So you can kind of scroll through this notebook and see stuff that was similar to what I asked you to try and some of my own commentary and thoughts on it. And, you know, from this point, ooh, that one's really nice. Love that curve. Anyway, you can, of course, go through the rest of these notebooks as well and kind of push yourself towards understanding some of the more complex features of neural networks. I hope this is a good springboard for you. And then I'll do my little advertising plug. I'm teaching a class that goes through all of these. It'll be very similar to what we just did together, except it'll go through most of the notebooks. You can find that here at aicamp.com, and I'll send that to the chat. It's let's see, starting at the end of the month, April 28th. So you got a time to prepare and think if you want to take this class. It'll be pretty fun. Any, you know, questions or comments you have at closing time?
I do. So who would be like this class for ideally? And also like what do, so this topic was called deep learning.
Mhm.
So what kinds of roles are out there for people doing this stuff, AI, deep learning, and machine learning? How do you how are people hired? Okay, you are a deep learning engineer, or you're just an AI engineer, and they kind of do different stuff based on the projects. And what are they doing day to day? Are they, yeah, what are they like? Are they working on these? They just pick up these models, or they build the models? Or I should say algorithms. So yeah, all those kind of clarity on what they kind of do.
Cool. Okay, so for the class, we expect, you know, levels between your two levels, which I think are pretty different. Brian, you've done some machine learning in the past. Aziz, you haven't, but you speak Python. You were able to figure out and use this library. Anyone who's at or above your level, Aziz, I think would be perfectly fine taking this class. Its focus is on the computer vision side of things, so lots and lots and lots of image processing, all using Keras and these deep learning models. In terms of what work kind of looks like for these folks, there are some people who are doing just deep learning, but it's more common for you to have deep learning as one tool in your belt as like a data scientist. So a data scientist is going to be building lots of different kinds of models, evaluating a few different models, and then a deep learning model might be one of them, a decision tree might be one of them, a k-nearest neighbors style model might be one of them. You perform, you know, comparisons of their performance, and then you say, I think this model's the best one. Maybe it was the decision tree this time around. Let's go to production with that decision tree. This could either be to say, make like an application that does inference live. You know, we could be, say, doing weather reporting, and we're working for the weather service, and we're picking a model that we think is best at putting out the 7-day forecast. That kind of a thing, something the data scientists might do. Looking at stock markets, that's something the data scientists might do. And you might either be, like in the stock market example, you could either be writing an AI that does stock trading, you know, autonomously, but you might also just be generating reports that inform humans' stock decisions. We have this model, its predictions are XYZ, here's 2 or 3 of those models, look at all of their predictions, and then have a human make the final say, the final decision. For deep learning specifically, the types of roles that are available for people who want to be, you know, explicitly focused on deep learning, not kind of machine learning generalists or data science generalists, those are going to be like self-driving cars is a good example. You could work on the self-driving car team. Your main role is taking the video feed and making decisions about what you see. That's a speed limit. It says 30, not 80, not 70. That's a human. That's a bicycle. That's a dog. How do I avoid each of these things? That's someone who's almost certainly doing explicitly and only deep learning, probably with convolutional neural networks on video feed data. Similarly, a lot of natural language models are now almost all deep learning, but there's other stuff too, you know, like Markov models and stuff like that. So in the language processing field and the audio processing field and the video processing field, you'll have more of a focus on deep learning right now anyway. It's the flavor of the decade. But a new decade's coming, it's just arrived, and there might be a new flavor this decade, who knows. So that's the kind of work that you'd see with clean, explicit focus on deep learning.
I know some recommendation engines as well are moving towards the deep learning side of things using implicit feedback data.
Okay, that makes sense. Yeah, stuff like Netflix.
Yeah, when they switched to thumbs up, thumbs down, I think they also switched to deep learning focus for the recommendation engine.
Totally. And deep learning, you know, deep learning is getting popular alongside improvements that we've made on the like hardware land, computational hardware. So these models have existed for a long time, but they're only now applicable because we have enormous computational resources. So there's some concern among some people that, you know, Moore's law has pretty much slowed down. We're getting to a physical limit of how small we can make transistors. So we need to be clever about, you know, switching to GPU style architectures or tensor processing units you might have heard of, TPU style architectures. And now when I use the word architecture, I'm talking about like physical hardware architecture, like computer architecture. And so if something weird happens and we can no longer find ways to improve the speed, then some of the other models that don't take as many computational resources as deep learning could again become more popular. But honestly, I think even though Moore's law is slowing down, there's still lots of clever stuff we can do with parallelization, and the implementation on the back end of these models is highly parallelizable. You know, you can process a batch completely in parallel, right? You just do the same matrix operations on each 784 pixel vector, and you can do all 28 of those independently, so you can do that process really highly parallelized. So there's still, you know, more incremental speed gains we can get out of the hardware that'll keep this model, I think, popular for a while.
Does Keras have parallelization built into it, or is it something that you have to implement separately?
It's built in from scratch, and same thing with TensorFlow. So what happens is the Python code that executes actually emits highly parallelized compiled C code, which then executes. So you can just plug in a GPU, you just go buy a commodity GPU, plug it in your computer, and the TensorFlow code will work. And you just have to, I think you do a little bit of configuration to say like, hey, talk to my GPU instead of, hey, talk to my CPU.
Yeah. Okay. Cool.
Sweet. Anything? Go ahead.
How did you learn all this? Since it's a new world, how do people like you like bring yourself up to speed when things are like new stuff like this?
When you're on the cutting edge, it's a lot of like paper reading. I took a class at a school called the Bradfield School of Computer Science. They also offer lots of, you know, computer science classes. But I also, when I did my undergrad, I took an AI course, and we didn't do much machine learning, but we did reinforcement learning, which is similar. So I had some good foundation from my university days.
And yeah, and then building up from there is if you practice it, you kind of get yourself up to speed then.
Exactly. And I plugged into a lot of like email newsletters and stuff. So I get, you know, so-and-so did a new model that achieved this new benchmark, blah, blah, blah. And I can go click on it, read the paper, see what the architecture was. And once you have kind of this basic foundation, reading those papers becomes a lot easier just because you're not so lost in jargon.
Yeah, true. Cool. I thank you so much for this class.
My pleasure.
That was great.
All right.
All right. See
Take
you
care.
later.
Take care. Bye.